Hi there, and welcome to the lecture video for section 1.2 on the topic of Gauss-Jordan elimination. We saw a little bit about this process, this Gauss-Jordan elimination in the last video. We saw that it is good for finding solutions of systems of linear equations. That's what we used it for. What we didn't see in that video, but we will see in this video, is that that's true whether the solution is unique, whether there are many solutions, or whether the system's inconsistent, no solution exists. So it really does apply when we have any number of equations and any number of variables, and that's what we want to explore here. What does it look like when we get not just a unique solution like we saw in the last video, but maybe many solutions or no solution? What happens with that Gauss-Jordan elimination in those cases? So let's remember that when solving using an augmented matrix, we try to use row operations to transform our augmented matrix into a simpler form. Ideally, in the cases that we saw where that was a unique solution to our system, that form that we tried to achieve had the identity in the left square of this augmented matrix, and the right column that remains there is filled up with all the solution values. Now, if the solution is unique, this is the case that we saw in the last video, this identity on the left side and solution on the right side is the reduced echelon form of the augmented matrix that we started with. So this is a definition, the reduced echelon form. It's very common to call this reduced row echelon form. Our book typically leaves that out, I believe, the row word. So I do want to talk about this for a minute, but let's note first that if there is not a unique solution, the reduced echelon form of the matrix will not have this form. You can go through all your row operations and the reduced row echelon form will not have an identity here. It will be closely related maybe, but it won't be an identity matrix there. That identity only shows up when the solution ends up being unique. And we want to explore today in this video, what happens if that can't be made into an identity using these row operations? What happens? Before we do that, I do want to talk about terminology a little bit. This reduced row echelon form, our book is a bit atypical in how they describe this form. Our book usually doesn't leave out doesn't have the word row. It usually leaves that out. And you might refer to this as REF, according to our book. Reduced echelon form. Most books, and most sources you'll run into, would leave that word row in here, and so they'd refer to this as reduced row echelon form, where you have two R's here, right? Reduced row echelon form. So our book refers to these things a little bit different than most. In most books, REF means simply row echelon form, not reduced, simply row echelon form. Which is something different, right? This REF we use, most books use it a little bit differently. So if you're looking for other sources on this stuff, just beware, when we say REF, the R means reduced. Other sources will put two R's there when they want the reduced version. It's kind of an unfortunate piece of terminology in our book, but we'll just have to make do with that. If you have questions about it, let me know. We can clear it up more. So let's look at a matrix here, a definition of a matrix here that is in this REF form. This definition is not going to be too hard to understand, and I think it's going to be easiest to understand by example, actually. Let's talk through it. A matrix is an REF form, this reduced row echelon form, if all these requirements must hold. If any 0 rows are all at the bottom of the matrix, meaning any rows that have only zeros in them occur at the bottom of the matrix. That's one requirement. The first non-zero element in each row is a 1. We call that a leading one. We discussed that a little bit already in the previous video. Requirement 3, the leading one of each row after the first row is to the right of the leading one in the row directly above. So visually, what I'm thinking of is, say I'm in my first row and I have a leading 1 here, and there's some other entries, doesn't matter what they are. In the next row, I must have a 0 below this guy, because the leading one in the next row has to be to the right of the leading one in the previous row. So if the leading one in the previous row was first column, in the next row, the leftmost column that I can have my leading 1 in would be here, to the right of the previous one. So something like this is acceptable. Something like this would not be acceptable. That's no good. Other things that would be acceptable and still satisfy this third rule we're looking at, this third requirement, would be having 2 zeros here, and then maybe your lead 1. Because still, when I went down a row, my lead 1 moved to the right, in this case to the third column. So long as moving down a row takes your leading term to the right, you are satisfying this third requirement. The last requirement is that all other elements in columns containing a leading 1 are 0, meaning in this sort of picture, above this 1, I would have to have a 0 here. And if there were any entries below this, if there are more rows below this, everything below this 1 would have to be zeros. Same with this guy over here. Right? That's a leading 1. Everything below and above it must be a 0. And here you could have other stuff, I suppose. So let me just go up with zeros. So those are requirements. Let's check out some examples to really see what we're talking about with this reduced row echelon form. It's going to become very important to be able to look at a matrix and tell if it's in reduced row echelon form. So you're just looking to meet all these requirements. So let's look at some that are in this form. This first set of examples, a bunch of matrices down at the bottom of the screen here. 108, 012, all zeros at the bottom. That certainly meets all the requirements. There is a 0 row, but it's at the bottom. The first non-zero element in each row, moving from left to right across the rows, is a 1. First row, moving left to right, first entry's non-zero, but it's a 1, so that's okay. Next row, moving left to right, as I go, the first non-zero entry occurs in the second entry here. That's a 1, we're good there. And in the bottom row, there is no non-zero entry, they're all zeros. So we met the second requirement. The leading 1 in each row after the first row is to the right of the leading row and the leading 1 in the row directly above it. Certainly that's true here. As we go down a row, the leading 1 is now to the right of the leading 1 in the previous row. And let's see, yeah, all other elements in columns containing the leading 1 are 0. Here's a leading 1, all the other elements below it are 0. Second row, here's a leading 1, all the elements above and below are 0. In the last row, there is no leading 1, so nothing, no extra requirements there. And this 2 and 8 are perfectly fine. So this is the sort of form that we might end up with, and after doing this row reduction, we might end up with something like this. Instead of that identity in the left square that we're used to from the last video, we might end up with something like this if there's not a unique solution to our system. We'll see how to unpack that and interpret the result, but we're seeing we won't always be able to put an identity here. It turns out that if you start with a given coefficient matrix or a given matrix of any type, there is a unique reduced row echelon for it. Reduced row echelon form. If you get to a form that satisfies all 4 of these requirements, it is the only form that satisfies all 4 requirements that you could have arrived at from that original matrix. Excuse me. So let's look at a couple more of these examples. The next one, that certainly has that nice identity in the left square, the left 3 by 3 square, and then a column over here. That is sort of the ideal example of a reduced row echelon form matrix. Certainly we have that stair-step pattern of the leading ones. They are all ones there in the leading entries. And everything above and below a leading one is 0. That's good. That's reduced row echelon form. This one here, there's only one column. The first row has a 1 in it, meaning all the 0 rows are at the bottom of the matrix. That's good. That leading one there has zeros all above and below it, so we're satisfying all the other requirements. Yeah, this one's reduced row echelon form as well. So it looks very strange, but still reduced row echelon form. The next one is as well, leading ones. As we go from one row to the next downward, the leading one moves very far to the right, but so long as it moves at all to the right, that still works. And everything above and below those 2 leading ones, this guy and this guy, is 0. So that's good. It meets all our requirements. And this guy's more complicated, but still meets all the requirements. Notice this 5 and 7 are not above or below a leading one, just above some zeros. So it's perfectly fine to have them there. And the leading ones follow this stair-step pattern as we move down. Now, more interesting is to look at things that are not REF. They are not reduced row echelon form. So let's look at these 3 matrices. What's wrong with this one? If we look at this matrix, we want to figure out what's wrong with this guy. The problem here is that there's a 0 row, that's the middle row, but it's not positioned at the bottom of the matrix. So we failed the first requirement. The next one over here, the second row, the leading term is a 3, not a 1. So that is not in reduced row echelon form. We'd have to scale that row by 1/3 to turn that into a 1. We'd have to do a row operation. It's not quite in that correct form. The 3 and 4 over here, those are fine. The 2 here, that's fine. Those are not above a leading term. So you're going to have numbers remaining there. What's wrong with this next one? Why is this not REF? The reason this one's not is because we break our stair-step pattern in the leading ones. From the first row to the second row, we do move to the right with our leading one. But you go down to the next row, and all of a sudden you have to move back to the left to get to your leading one. This is not reduced row echelon form. To put it in that form, we'd have to interchange rows 2 and 3. Switch these 2 rows out and it would look good. Finally, maybe take a look at this last one. Think really hard about what's wrong with this picture. What else could we do to this to meet all these conditions up here? The problem here is that this 7 is above a leading 1, so it must be cleared out. We must take the first row and subtract off 7 copies of the second row to get rid of that 7 in the first row. That would put it into reduced row echelon form. So we really do want to practice this, kind of looking at a matrix and knowing what conditions to check off in our mind to really identify if it is in reduced row echelon form. If it is, there are no more row operations that we can do that will leave it in this form. No more non-trivial operations. We could scale a row by 1, but that wouldn't change it. So that's what I've been getting at here, this note that the reduced row echelon form of a matrix is unique. No matter what order you apply all these different row operations to get it into this form, once you end up in a form that meets all 4 of these conditions, there's nothing else you can do. You are stuck with one option that you could have ended up at. It's a very, very useful fact here. So Gaussian elimination is a systematic process to produce this form. I should say, let me fix this in my notes here, Gauss-Jordan elimination. Gauss-Jordan, let me fix it completely. It's not Gaussian, it's Gauss-Jordan. Gauss-Jordan elimination is a systematic process to produce this form from a given matrix. So how do we solve systems using this? what we're going to do is we're going to write down the augmented matrix corresponding to the system of equations we start with. We saw some examples of that in the previous video. And then we are going to derive that reduced row echelon form by creating lead ones, then zeros above and below each of those leading ones. And we do that column by column. So I'll start in the first column, make sure there's a lead one in the top left, zero out everything above and below it using row operations. Then I move on to the next column. I want to make sure I put a lead one there and use that to clear out what's above and below it. You might need to swap some rows as you go, and we'll see examples of this, so it'll hopefully become clear what I'm saying. But we just systematically put it into this form. Take a lead one, clear out everything above and below it. The next row, take the next lead one, clear out everything above and below it. And finally, after we've got it into our reduced row echelon form, we are going to unpack it again back into the system of equations it represents, which will just have been reduced down to its simplest possible form. It won't necessarily be obvious what the solution is if it's not a unique solution, right? In a case like, which was it, this one up here, if we did our reduction, we got to this form, we could read off the solution would be 739. If that reduced row echelon form is an identity matrix. But if it's not, if we get some of these weird matrices like this at the end of the day, we're going to want to see how to unpack that into a system of equations and determine and write down a solution from that. So let's take a look. Let's take a look here. Kind of hiding some of the details here. I want to go through the work with you on this one. Let's look at this system of equations. Right? X1 plus 2x2 plus x3 equals 7, x1 plus 2x2 plus 2x3 equals 11, 2x1 plus 4x2 plus 3x3 equals 18. I want to see how to use Gauss-Jordan elimination to solve this system. So I'm going to start out just by using this augmented matrix for the system. I create this just by taking all the coefficients, just peeling off all the information from this system, leaving the variable names, and the plus signs, and the equal signs behind. So I get 1, 2, 1, 7. It's the coefficients, and then the right-hand side. That's my first row. 1, 2, 2, 11. Coefficients in the right-hand side of the second equation go into the second row, and so on. So let me take this matrix up to the top of my page here and do some work on it. Oops. We want to see what is this Gaussian elimination, this Gauss-Jordan elimination that we've been describing. Now, in the last video, I described what we were doing as Gauss-Jordan elimination, but I'm going to kind of take a little bit of that statement back here. We're going to see why. Gauss-Jordan elimination is actually a very specific algorithm, very specific process that's commonly used really analyze the computational requirements of actually solving a problem like this. How many mathematical operations are you doing? Well, you make a systematic process to actually do it, this Gauss-Jordan elimination, then you can actually count the operations involved. So if you're programming a computer to do it, you know what to expect from the requirements on that computer, right? How hard it's going to have to work, how many operations it'll have to do. But we're going to see that for that reason, Gauss-Jordan elimination is actually very rigid. It doesn't leave you a lot of freedom like we had in the last section to solve these things more in a kind of clever way. Gauss-Jordan elimination is going to say very specifically what you have to do at each step. You use the lead one that happens to already be here. If there wasn't one, you'd want to rearrange your equation, swap some rows to put a lead one here, or some non-zero so you can scale it to be a 1. But here we already have a 1. We want to use that to zero out what sits below it, the 1 and the 2. So I'll do that with row operations. I'll take row 2 minus row 1, put that back into row 2. Right? Because 1 minus 1 is 0. That'll work. And to get rid of the 2 down here, I'm going to take row 3 minus 2 copies of row 1, put it back into row 3. So what do I get? I'm not changing the first row. The second row becomes 0 here, right? We're just subtracting second row minus first row. So 1 minus 1 is 0. 2 minus 2 is another 0 here. 2 minus 1 is 1, and 11 minus 7 is 4. On to the next row. 2 minus 2 copies of 1 is 0. 2 minus 2 copies of 1. 4 minus 2 copies of 2 is 0. 3 minus 2 copies of 1 is 1. 3 minus, yeah, that's right, okay. And 18 minus 2 copies of 7, 18 minus 14 is 4. Okay, well, this is okay. The first 2 rows are looking actually pretty good. We have a lead 1 in the top left, zeros all below it. In the next row, the first non-zero entry does move to the right of the previous one. This guy moves to the right to get to the next one. And so we're in good shape for the first 2 there. Now look what we can do though. We can get rid of this entire bottom row using the one above it. If we were going through the usual process and using this guy now to clear out what sits below it, look what happens. We would take row 3 minus row 2, put the result back into row 3. And oops, made a mistake there. And notice row 3 is exactly the same. So when we subtract row 3 minus row 2, we get all zeros here. And this is very close to reduced row echelon form. Take a beat here and maybe think, what's left to do? What requirement have we not met here? I claim the requirement we haven't met is this lead 1 in the second row doesn't have all zeros above and below it. This guy up here, this 1 above it, needs to be removed. So I'm going to use this guy to remove the 1 that sits above it now. What will that take? That will take row 1 minus row 2. You can put back into row 1. 1 minus 0 is 1, 2 minus 0 is 2, 1 minus 1 is 0, 7 minus 4 is 3. And that's all I changed. Okay, that's it. This is our REF form. Now, why is this useful? I claim all we've done is kind of cleaned up our original system to its simplest possible terms. We have canceled out everything we can. In fact, we got rid of an entire equation, right? That might not be clear yet, but let's see why I say that. We unpack this now back into a system from the augmented matrix. So the first row of our matrix would actually unpack into the equation x1 plus 2x2 plus 0x3, which we don't even have to write, equals 3. Next line, 0, 0, 1, 4, that row would read 0 times x1 plus 0 times x2, don't even have to write those, plus 1 times x3 equals 4 on the other side. And notice what the bottom row says. It says 0x1 plus 0x2 plus 0x3 equals 0. Well, the left side does equal 0, right? 0 times all those variables is 0 when we add up. So notice here, all we're left with for that third equation is a trivially true statement. Meaning it doesn't tell us anything. It doesn't impose any restrictions on our x1, x2, and x3 solution values. It's just an extra added in equation that adds nothing. So we can actually get rid of this. No matter what we choose for our variables, it's always going to be true that 0 equals 0. This last equation is always satisfied. independent of our x1, x2, and x3 values. We drop the equation completely. And we're left with just these two equations. Now, this is different than what we've seen in the past when we had a unique solution to the system, right? When we have a unique solution in the REF form, the left square here would be an identity, the right column would be our solution values. This is different. This didn't unpack into x1 equals some number, x2 equals a number, x3 equals a number. This unpacks into a kind of tangled up mess still. So how do we handle it? Well, these variables in each row, once we're in our REF form, we can look at the lead variables, x1 and x3. Right, in the first equation, x1 comes first. We're going to call that the lead variable there. That's the first non-zero coefficient variable in this equation, moving left to right. x1, that's a lead variable. x3 is the first remaining variable in the second equation. These we call lead variables or leading variables. And any other variables that are not leading variables, this x2, for example, we call that a free variable. In this case, we have one. In other cases, we can have many. Okay. So what can we do now? The idea from here is express lead variables. Handwriting got sloppy there. Leading variables, I'll say. In terms of free variables. So let's see what that looks like. In the first equation, our leading variable is x1. So we solve for that in terms of the free variable x2. Well, we just move that equation around, subtract the 2x2 to the other side. And this first equation tells us x1 is 3 minus 2x2. Our second equation is already solved for the lead variable. It's already got it isolated there. And so there we have it. Now, what are we really going to say here? We're going to say, let's see how I phrase this down here. Yeah, this is the point they're at. We solve for the lead variables in terms of the free variables. We got x1 was 3 minus 2x2, x3 was equal to 4. Notice that's exactly where we left off. So I'll pick up from here. Well, there are many solutions in this case. For any value of x2, I can plug that in here and find the x1 that goes with it, and I know x3 is always 4. So really, there are infinitely many solutions to this system, and we're just trying to find a good way, a clear way, a useful way to describe that set of solutions. Right? But there are infinitely many in this case. The general solution is obtained by assigning arbitrary values. We use symbols like R, S, and T for this, to each of the free variables, and express the leading variables in terms of those arbitrary values. We actually call those values parameters. This R, S, and T are parameters. So what does that look like here? All we're going to do is say the free variable x2, let's call that a parameter, one of these symbols here, just some arbitrary value. We can express the solution x1, x2, and x3 in terms of that value. So what do we get? Let's use R for this x2 value. x1 is 3 minus 2x2. Replace the x2 with an R. So x1 is 3 minus 2r. What is x2 in our solution? x2 is r, right? That's what we let it equal. We just replace this with an r directly. So that is our r value. And x3 we've already seen equals 4. Right? What we're saying is that this is an explicit formula for the x1, x2, and x3 values that will solve our system. Plug in any value for r, any real number here, and x1, x2, x3 that you get out of these formulas will solve this original system up here. Right? We have infinitely many solutions in this case, this is a nice way to describe them. We call this a parametric description because we call this R value, this arbitrary value for R that we replace the free variable with, we call that a parameter in general. And you may have more than one free variable and thus more than one parameter. That's why I listed out a few here, like R, S, and T. In the case they had more than one free variable, you'd have to use more parameters. Okay. And right away, before we go any further, I'm going to write down a pretty useful way to express the solution here. Let's express it as a column matrix. We're going to talk about vectors more soon, but it turns out these, I guess we don't even need to talk about vectors for this. We'll see that matrix mathematics allows us to break up a column matrix like this and rewrite it as, kind of decompose it. We could write this as 304 plus, we'll see this soon. We haven't seen it yet. I'm just kind of jumping ahead and giving a little preview here. Plus all the stuff that has an R in it. And the way I'd really like to think about this is really being, again, we'll see that this sort of manipulation of our symbols is allowable with matrix math. We'll see that soon. You can write this as R times this matrix, -210. It's kind of like you're factoring an R out of this. So the way I like to think about this is that our solution is really this fixed matrix, 304, plus any multiple R of this other fixed matrix. Right? If you're thinking maybe a little ahead to vectors, think of these as vectors in 3D, if you're familiar with those. Right, so I think of this as being a fixed vector plus any multiple of another vector. It turns out, maybe this looks familiar, this is actually the equation of a line in 3D. I've used columns where I think our typical calculus sequence uses rows for vectors. But this is really the right form for an equation of a line in 3D. It turns out what we've got up here is three planes which meet in a line. So there's actually infinitely many solutions and they all sit along a line given by this description. We'll get into that more, but I wanted to look at this idea right away of writing a solution this way, broken down into the parts that have a variable R and the parts that don't. We'll get into that more, but that's just a little preview of what's to come. Okay, so let's look at another example here. Assume the reduced row echelon form of the augmented matrix is what's given to you and solve the remaining system that it represents. This is down at the bottom of my screen down here. Let me jump over to the side so we can do these together here. In part A, I have the augmented matrix 1, 0, -3, 4, 0, 1, 2, 8, and all zeros. So we want to solve the system whose REF augmented matrix looks like this. Right, so it's like we're skipping to this step of the previous problem and we're solving from there. Right, you've seen how to do the reduction. It'll take some practice, but I don't want to waste your time showing you row operations over and over. So let's jump in and try to solve from here and see what happens. If I was to unpack from here back into the system this represents, it would be x1 plus 0x2, which I don't even write anymore. I'm not going to write those, the zero coefficient variables, minus 3x3 equals 4. X2 plus 2x3 equals 8, and 0 equals 0. So if we want to solve this, remember what we do. We look for the leading variable in each equation. In this case, that means the x1 in the first equation and the x2 in the second. Leading variable just means once you're in REF form, looking left to right across the equation, what's the first variable you come across that doesn't have a zero coefficient? In the first row, that's x1, and the second, that's x2. So from here, all we're going to do is say that any variables remaining are free variables. So x3 is a free variable. We let the free variable equal a parameter value and solve for the leading variables in terms of that parameter. This will give us our general solution. So if we do that, the first equation becomes x1 equals this 4 that's already on the other side. I'll add the x3 to the other side. But remember, x3 is just r. The next equation, I have x2 equals, I've already got 8 over here, and I'm going to subtract 2x3. But x3, remember, again, is r. And finally, I do want to write down what x3 equals. It is r. That gives me my full explicit expression for x1, x2, and x3 that solve my system. Plug in any value of r, you have a solution triple for that system. And if you wanted to practice breaking this down like I did the last solution, claim this is what we get. See if you can work through the details. See if you agree with this. To break this down the same way we did the last one, I think you would get 480 plus r times 3 negative 2, 1. Again, this one's the same situation we saw before where we have a line of solutions. This is the equation of a line in 3D. Every point on the line is a solution. It's the intersection of the 3 planes that our original equations represented. So let's do this again with one more, this matrix B that I have written here. Let's see this one. I'm gonna just kind of walk through this. So in the first step here, I really just unpack the matrix into the system it represents, right? 1, 0, 2, 0, 3, 6 means I'm skipping the x2, I'm skipping the x4, but I do have 5 variables here if this represented a system. And from there, I just look at, I assume this is already in the REF form. It is, you can check that. But I look for the leading variables. The first equation is x1, second equation lead variable is x2, third equation is x4. And if I look at that, that means x3 and x5 must be leading variables. So all I want to do is let x3, that's a free variable, let that be my r, and let x5, that's another lead variable, that's also a free variable, so it should be called a parameter, but we don't want to use the same r. Let's use some other letter. I'll use s. I don't want that to look like a 5. There we go, s. Okay. And the idea is solve for all the other variables in terms of those. So x1, just looking from the first equation, is the 6 that's already over here, minus 2 times x3, which is 2r, and minus 2 times x5, which is 3s. x2 says just solve the same way for x2. So 7 minus 5x3 minus 4x5. That's just minus 5r and minus 4s. Same for the x3. That's easy though, it's just r. x4 we want to solve for as usual. Negative 3 minus 9x5, so 9s. And x5 itself is s. So in that way, we do get this completely explicit formula for the solutions x1, x2, x3, x4, and 5 that will solve the system this augmented matrix came from. I do want to do this one more time since I think it's important. Let's see how to decompose this the way I've mentioned a couple times. We write our solution as a column matrix. We can write it as 6, 7, 0, negative 3, 0, plus r times negative 2, negative 5. This is a little different than before because we have 2 free variables. 1, 0, 0. Again, if this isn't quite clear, that's totally fine. We will do much more explanation of what I'm doing here once we've talked more about matrix operations. For now, I'm just, again, giving you that preview of what we're going to be doing with these solutions later. Okay. And so it turns out, just like when we had a single free variable here, this represented a line of solutions. When we have two free variables, R and S here, that actually represents a plane, right? Everything kind of spanned by these two different lines, so in this case, this is actually a plane of solutions, since it's two-dimensional, two free variables here. It's a plane of solutions in fifth dimensional space. Kind of hard to picture. Okay, let's go a little bit further from that example. And see this one over here in my bottom right-hand corner. Again, I'm hiding the solution from you. It's in my notes for your reference later, but I'd want to work this one out with you. From, I guess I don't have to copy this matrix, from this augmented matrix, this is part C here, the system this represents is what I'm writing down now. And notice the bottom equation. The bottom equation would say 0x1 plus 0x2 plus 0x3 equals 1. What's going on here? 0 times all these variables is just 0 here. We have 0 equals 1. That is not true. Regardless of the x1, x2, and x3 values we have, 0 equals 1 is never true. We can never satisfy these three equations, regardless of how we choose our variables. We cannot make 0 equals 1. We cannot make that a true statement. So this is inconsistent, no solution. So I want to recap real quickly what we've done in this three-part example here. We've seen how from the REF form, we can unpack that augmented matrix and solve the system it represented. We've seen in the previous video how to do that if there's a single unique solution. In that case, the sort of reduced row echelon matrix we would get would have that identity in the left square, in which case reading out the solution, excuse me, is trivial. What we've seen here, though, is how that ends up looking in the case that we don't have a unique solution, but a general solution set in terms of these parameters, right? We've described how to kind of unpack that information from the reduced row echelon form of the matrix, and how to see what happens from that reduced row echelon form matrix when there is no solution. That'll occur whenever you have all zeros in your augmented matrix, all zeros in a row except the very last one being non-zero. That will always unpack to the equation 0 equals a non-zero constant, which can't be true. So we've seen how taking our augmented matrix, performing Gauss-Jordan elimination to get it to REF form, can be used to solve any system, any linear system, right? Whether it's a unique solution system, system with infinitely many solutions, or a system with no solution. All of that information can be gleaned from the reduced row echelon form of the matrix. So let's wrap up this section very quickly with a quick definition. A linear system is called homogeneous if all the constants on the right-hand sides of the equations are 0. So let's consider the system from part B, except with 0 constants in the REF form. So here's our system from part B, except let's put zeros in for the constant column. Right? This is like our coefficient matrix here. Here's our constants column. Let's put zeros there. That's what this example is saying. When we do that, we get this matrix instead. So if we were to unpack this back into equations, notice we'd have 1 copy of x1, 2 copies of x3, 3 copies of x5 equals 0 now. right? Having all zeros, and same for the next two rows, they would unpack to also have zeros on the right side. This form here is a homogeneous system because it has zeros all on the right side. And notice you can still unpack and find the general solution there. If I do this, I get exactly what I had before in terms of the parameters here, but notice how it's different from my solution that I did have before. See if I can find that solution. It is, oops, this stuff. Let me see if I can grab that. This stuff. There, I think maybe we can see it together. No. Sorry for my technical difficulties there. This system down here matches this solution we had up here for that same matrix that wasn't homogeneous, didn't have all zeros. The only thing that's different is in all of the right-hand sides here, our x1, x2, x3 through x5 values, we lost any constants that were over there when we switched to the homogeneous system. So notice we had a 6 out front of the negative 2r minus 3s. The negative 6 is gone now. We had a 7 up here in front of the negative 5r minus 4s. The 7 is gone now here. So those constant parts somehow came from not having zeros on the right-hand side. When you have zeros on the right-hand side, you'll lose those constant parts and only have this stuff in terms of your parameters. So that's a really unique fact here. Just a sec, let me try to get my screen correct. Yeah, we can think of really this solution that we unpacked from here to this sort of broken up decomposed form. Our solution still looks like this if we make zeros on the right-hand side of our equations, except when we do that, it gets rid of this constant column. Back the pen over here. Leaving just this stuff. So what I'm getting at is that somehow when you're solving a homogeneous system, you're getting all this kind of essential stuff that either makes a line or a plane. But when you have non-zero stuff, a non-homogeneous system, the 6, 7, negative 3 here, it puts a constant in before that and kind of shifts this line or plane away from the origin. Right? You have a line or plane of solutions. In the homogeneous version, that always goes through the origin of your space. In the non-homogeneous version, there's some constant shift here that moves that whole line or plane away from the origin. That's a really nice connection to make this. Somehow homogeneous systems can be solved to get kind of the basic space, the line or the plane, then the non-homogeneous system is just a shift of that away from the origin. Again, I might be describing things in ways that aren't clear in terms of vectors and shifting in space. That's okay, we're gonna go into that in much more detail. Just pointing in the direction we're going. But notice once we have all those constants gone, which will always be the case for a homogeneous system, right? The constants are gone on the right-hand sides of these solution values. That means since there are no constants there, plugging in 0 for the parameters shows us the 0 value for all variables will always give you a solution. If I plug in r and s equals 0, I can plug in any value for them, but if I plug in 0 for them, I get all the variables, all the unknowns must be 0. That gives us a solution. And since we know we'll never have those constants there, we'll always have stuff just in terms of parameters here in the case of a homogeneous system, we know all homogeneous systems have this property. It should be clear that all homogeneous systems have that property anyway, that the x1, x2, x3, x4, x5, all variables equaling 0 is a solution. That should be clear from this set of equations, right? If the right-hand sides are all 0, certainly plugging in 0 for all the variables solves that set of equations. So this is a nice fact. This is a theorem in your book. A homogeneous system of linear equations in n variables always has the solution where all the unknowns equal 0. That is called the trivial solution. it will very obviously solve the system. It's just not very interesting or useful in many cases. Right? Often there are many other solutions, but the trivial solution will always be a solution to the homogeneous system. Okay. And finally, let's finish up here. A homogeneous system of linear equations with more variables than equations has many solutions. That's exactly what we saw up here. There were 5 variables, x1, x2, x3, x4, and x5, yet only 3 equations represented. We have more variables than equations, and in that case, we have many solutions. The way I would think about this is that each equation is like a requirement of our solution, right? It's a new condition that we have to meet. It's an added kind of barrier to being solved. The more equations, the more requirements your solution has to meet. But the variables, I would think of those as giving you sort of more ease to meet those conditions set by the equations. If I have 100 conditions on one variable, that's hard to do. But 100 conditions on a million variables, that's not so hard to meet. In fact, it's very easy to meet that condition or those conditions. So the way I think about this is that the number of equations kind of constrains your ability to solve, but the number of variables kind of expands your ability to solve. So if you have more variables, more ability to solve than equations, than constraints on solving, then you should have many solutions. It should be easy to come up with solutions, lots of them. That is a very kind of hand-wavy way to talk about this stuff, but I hope it gives you sort of an intuitive sense of how to look at these systems and sense sort of what solutions to expect. The number of equations represents how hard it is to solve. The number, right? It's how constrained you are. The number of variables is how easy or how free you are. Okay, just a little numerical note here at the end. When we're doing these operations, these row ops, often our idea is to program these sorts of things into a computer to maybe solve a system. Well, when we do these sorts of things on computers, a computer can only represent numbers with so many decimal places, right? They have finite memory. So I can't have a number that has 10 quadrillion decimal places. That's just too much information to store. So these computers have limited, or what we call finite precision, which means that when we do some calculations on something that's an irrational number, we really get some round off error because we can't really express that irrational number. We cut it off somewhere and calculate with that. That's not going to produce an exactly correct value. So the more times we do that, the more that round off error compounds. And so it really means that when we can do some sort of operation or solve a problem with fewer operations, that's better. We're less prone to building up round off error in our solution. So if we do a lot of operations, we call these flops, floating point operations, then those errors, they propagate through the calculations and they get amplified in some cases. So fewer operations is always good. It turns out this Gauss-Jordan elimination to solve a system the way we have in the case of a unique solution really scales like if you have n equations and n unknowns, 1/2 n cubed plus 1/2 n squared multiplications, and 1/2 n cubed, sorry if you can't read this, minus 1/2 n squared additions. So if you were to add up going through this process, how many times you'd have to add or subtract, multiply or divide any two numbers, it would really depend on the number of equations and unknowns you have, but it's something like n cubed. So 10 equations in 10 unknowns would take 1/2 of 10 cubed plus 1/2 of n squared multiplications and 1/2 10 cubed minus 1/2 10 squared additions and subtractions. But those are big numbers. Those are thousands of operations we're talking about to solve 10 equations and 10 unknowns. Now, if you start thinking about a situation in real life where you're gathering huge sets of data and trying to do things like this, you can imagine maybe many more equations and many more unknowns, where these numbers get huge very quickly. They scale like the cube of how many equations and unknowns you have. So that grows very quickly. It becomes very important to use efficient methods to solve these. Efficient meaning they require the fewest number of operations as possible. Not only does that help with round-off error, getting accurate results out of a computer, but it also, of course, will be faster to compute if we don't have to do as many computations. Okay, I think that is it for this section. Stay tuned for the next video in which we'll talk about some more row operations, not quite Gauss-Jordan, but maybe something a little more practical. We'll see that in the next video. Thank you for your attention.